the captain will let me.
Keith, the floor is yours, sir.
Okay. And we'll take it over. Okay, so I'm going to share my screen now. And we'll go into the full PowerPoint. I'm sure what everybody needs are more PowerPoint, right? Okay. All right, so in my time, I'm going to go over information about global climate models.
Your screen isn't being shared.
Is it being, now is it shared?
Now it is.
Okay, there we go. Okay, so I'm going to be talking about global climate models and with an eye towards just some background information that I find that some folks involved with the use of climate information for adaptation to climate impacts work find informative or surprising, and also delve into a little bit of the ways that some of the information can be used well, and some of the common mistakes in assuming that when people kind of treat model output a little too similarly as they would observation. So basically the general theme is I'm going to be looking at different spatial scales and time scales. There you go. We were asked to give a little background on how we got to where we are today in the background. So I'm in my mid-50s, so that means that my general interest in science happened to come about at the time when, for me, when the second man stepped foot on the moon, because he was from 2 towns over from where I lived, just a couple miles away by Waldron. And then that was in '69. And then the next year or so after that was the world's first Earth Day, which just generally took my science interest and helped move them over towards what's going on with our own planet and the environment. So I ended up going to Rutgers here in New Jersey, where I am now, and got degrees, undergraduate and graduate degrees in meteorology. And like a lot of folks, I don't know how many of you got into the field as a meteorology type major, a lot of weather leanings there, which means folks who are interested in forecasting day-to-day weather. And I did a little work for a year or so as a radio broadcast meteorologist, which was interesting, but I actually found that around that same time, opportunities I had to do a little consulting work where I was helping to do some forensic climatology and preparing testimony, and also by working with New Jersey agricultural meteorologists. I enjoyed kind of that interface even more that involved doing research and then taking that information and finding ways to convey it to folks who are interested. So that's the general background. And I was kind of lucky that I had an opportunity to go straight from school, straight from Rutgers, to get a job here at the place we know as GFDL here in Princeton, which for those who may not know is the place where the world's first global coupled climate model was created back in 1969 by the 2 gentlemen pictured here, Suki Manabe Standing and Kirk Bryan. So Kirk was my first boss here, and then about 10 years into my tenure at GFDL, Kirk retired and moved into Suki's group. And those were just like pillars in the field, and it was a great place to come and work on really world-class cutting-edge research. And it was a little intimidating, but it's been a good thing. So now I get to the part where I get to feel old, where I notice that I've been here for over 30 years. But I think what that's relevant for you folks is just to keep as early career folks is that even though I haven't moved, and most people move from job to job, I haven't moved, but the job itself has changed a lot, and so has the public perception of it. When I started, the kind of work we would do here was pretty much only of interest to folks who read scientific journals, peer-to-peer type information. But as time went on, the kind of climate research we did and the science that was involved behind it was something that we would find constantly in the news and of great societal relevance. So, the work has changed somewhat, but the public perception even more. And so maybe a takeaway message you all can have early in your careers is that there's a limit to your career predictability. You may think you know where you want to go now, but it'll be different. The landscape will change in the coming years. Okay, so a little bit more onto the meat of the talk, where I'm just going to note here that even though I will be focusing on global climate models, that progress in the field of physical climate science occurs as a combination of 3 things come together: observations, theories, and numerical modeling. If you think about the really milestone, big picture breakthroughs that have come through in climate science over the past few decades, it's really when those three things, observations, theory, and modeling, come together and tell a consistent, compelling story that becomes multiple lines of evidence coming together in a certain way. So some of the kind of conclusions you can think of in just the past 10 years or so, the idea that it's unequivocal that the planet's climate is changing, that most of the warming that's been seen on the planet for the past 50 years or so can be attributed to human activities, and that given our understanding of the climate system, the way it works and what people are doing, you can probably expect there to be more climate change in the 21st century than was witnessed in the 20th century. So those are three big take-home messages, and we get a consistent story there. But you'll also notice that all those things I just mentioned are referring to things at a very large spatial scale. Planetary changes, or how the continents will warm more quickly than the oceans, or how the Arctic might warm about twice as fast as the tropics. And we also tend to talk about things on multi-decadal timescales, 50, 60, 75, 100 years. And one of the issues with that is that's a fine starting point. There's compelling evidence that is then putting climate change and the science behind it on a lot of people's personal radar, beyond just the journals. But one of the things that happens is as the topic of climate change gets on people's radar screens, they then ask, well, what does it mean for me in my backyard? What does it mean for the things that I care about? So that's a not so subtle change in the question, the scientific question that's being asked. Often in impacts work, we go from dealing with those large scales where we built up this confidence to asking questions about smaller spatial scales, often on shorter time scales. And the questions aren't so much about how the basic physical climate parameters of temperatures, winds, precipitation are changing, but more what does that mean for the agriculture, the ecosystem, the water resources, the human health aspects that we care about. So each of those ways, we're introducing additional challenges as we try to take this information and make it more relevant for people to make well-informed decisions. So just kind of recap this part, there's these three traditional climate science questions. Is the planet climate changing? A question of detection, yes, unequivocal. What's causing it to change? Well, most of it for the last 50 years due to human activity, but there's certainly a role for natural variations. That's something known as attribution science. And then the attributions is something where we really, really need to blend observations and models along with understanding in order to do that attribution. But then we get to the part where people want to know about what's going to happen in the next century. So we can't rely on observations, we don't have observations of the future, and that's where then we really start to lean more on the global climate models as tools that can help us produce projections about how the climate, the physical climate, can change in the future given different assumptions, what-if scenarios about how emissions of greenhouse gases and other radiative forcing changes may occur in the future. So those first three questions lie squarely in the realm of the physical climate science, and then we end up with that fourth question that most of you may be interested in, is how might changing climate affect things that you care about? And that then is moving from the realm of pure physical science into that part of the sciences that you're interested in. We have to have that handoff of information across disciplines. So in general, what I'll try to talk about in the next half hour or so is we'll deal with the issue of climate. I'll talk a little bit about timescales. I find a lot of people, especially folks coming from various parts of NOAA, weather services and others, that word climate actually gets in the way. We use one word for many, many different phenomena, and it can be a little bit of an impediment to some understanding at some point. One of the takeaways is to try to match the tool to the problem. The physics is physics of the climate system and the weather system, whether we're interested in 5 days forecasts or 100-year timescales. But the actual tools, if you're using models, the way they're configured, the way the problems are posed, we need to match the tool to the scientific question being asked. Then I'll go a little bit into giving you an idea about where today's decadal to century, what Dixon stands for, climate models, how they're constructed, just a broad brush view, won't get too deep into the weeds, but also pose a question to you folks that you can think about even now, and maybe we'll get back to later, of if, how would you judge whether one climate model was better than another, what would you do to make the current generation of global climate models better? What would your metrics be that would determine what makes a better model?
It's his turn off, too.
Keith, yours turn. We hear you, but your screen popped off.
Really? Okay, I still have it
We see
here.
your GFDL logo.
Really? Okay, let me,
Just happened.
okay, I'll try to reconnect again. And in the process, we're learning something about government computers.
It's thinking now.
Is it back?
Yes. Yep. Yep.
Okay. Yeah, but I do not have anything resembling privileges on it. So anyway, NSA just kicked us off there for a little while. So we're back. Okay, good. Anyway, and then I'll close with some things that hopefully during the question and answer, I'll go off with your questions. Hopefully you have some, and a little bit about how we take the message that we can get from the science and how to convey that both in a way that's accessible, but sometimes guard against oversimplifying. Okay, so often when I speak to folks, I talk about matching the problem with the tool. You have to think about a lot of climate questions of interest to decision makers and the public can be divided into maybe two categories. There are people mostly interested in climate change mitigation, something that would cause a reduction in the amount of climate change that will happen in the future. Most often that's thought about ways of reducing greenhouse gas emissions. You can also have ways of enhancing the sinks of carbon dioxide or geoengineering would fit into that. But then there's other folks who are largely interested in adaptation. Climate is changing, it's going to continue to change. There's a good amount of it already in the pipeline. So given that, then what sort of actions might be taken in order to reduce the vulnerability of both natural and human systems to those changes are in the way? So while they're related, one has to do with limiting the amount of climate change, one has to do with about preparing for it, and different things that you could think about that are related or in response to climate change can fit into the different categories. Where that ends up having an issue as it relates back to the climate models and the questions we're posing and the answers we're able to give is this general question where some people use the phrase, we debate about how good it is, but the desire to go from the best available science to something that's considered actionable science. Given the state of the science today, what can be conveyed with some level of scientific certainty or fidelity that would be enough for people to then make their determination and how to factor the climate information into the vast set of other things that they're considering and making plans for the future. And it happened that a few years ago, I guess it was about 9 years ago now, I happened to spend 1 year where I made a number of trips down to DC, and it was kind of interesting that I talked to a couple of high-level staffers during that time on the Hill who had two very different ways of looking at what was happening in climate science and what climate science had to offer people. There was one very high-ranking person, he had been chief of staff for the House Science and Technology Committee for a number of years, who said, basically, climate science, as far as he was concerned, was done. That it had answered the main questions that policymakers had posed to it. Yes, the climate's changing. Yes, most of it's due to human activity, and there's more in the pipeline. So he considered that the ball was pretty squarely in the court of the policymakers to do or not do what they want. The basic parameters of what climate science needed to give them was there. But that's because he was mostly interested in mitigation, those international treaties and whether to have carbon taxes or things like that. At about the same time, there was another pretty high-level staffer who worked for someone who's now the governor of a western state, who told me that, I don't think you people, you climate scientists, realize what you've done. By putting out the answers to those same three questions, yes, the climate's changing, it's unequivocal, yes, it's mostly due to human activity, and yeah, there's more in the future. You've now created a demand for information that you're probably not ready to supply. Because people don't care what's going on globally, and they really don't care what's happening just the temperature. They want to know what's going on in their congressional district for the things that they care about. whether it's agriculture or transportation or human health, or go through the long list of things. So when the Navy is concerned about whether melting ice in the Arctic means they have to start making long-term plans on building a different kind of fleet to patrol it, that's an adaptation. They really aren't all that interested in the mitigation side. So just two different ways to frame the question, which brings us back then, what does climate science, or what does the climate model part of climate science have to offer? And one of the other common questions we can get from folks is like, why should I trust models? I work with models all the time. I know you can tweak them and tune them and get what you want. They're not that great. Now, part of that answer is that, well, not all models are created equal, but there is the part where we just need to recognize models are what they are. They are simplified representations of complex systems that we simplify things so that we can actually study them. Because the question we can turn around is how can we perform experiments on the global climate system? If I'm giving a talk in a high school, I point out that we can't take the Earth, shrink it down, stick it in a test tube, and do experiments that way. But that's not the kind of way that we can do science for climate. That may be what they're used to in their school, but that's not it. So instead, what we're doing is we're taking mathematical equations to represent the physics and other important components of the Earth's global climate system, converting that into computer code, and then our laboratory ends up being massive supercomputers, and our tools end up being these computer programs. So that's the environment in which we work, which disappoints a lot of students we talk to in schools, because they find that I work at a place with the word laboratory in their name, they want me to be wearing a white smock, but that doesn't happen either. So basically the way to think about it is these global climate models are going to be our virtual Earths. They're going to provide a physics-based method, and that's a key. We're starting with F equals ma, and we're moving from there, to estimate how the planet's climate will respond to changes in various forcing agents, things that change the flow of energy through the system. Greenhouse gases being the most important ones that we study, but there's a whole host of other factors as well. And we're not interested just in the atmosphere. A lot of people are surprised to learn that in a lot of the global climate models run around the world, half of the computer time or less is actually spent simulating the atmosphere. That we also need to spend a lot of time thinking about the ocean circulation, the sea ice, the land physics, and hydrology, and how all those different components exchange energy, mass, and other factors between each other. And that would be the traditional physical climate model, those four components: atmosphere, ocean, ice, and the land. Also, in the last 10 years or so, there's a growing part of the market share, I would say, of global climate models that actually now go under the name of the Earth System Model, where in addition to the physics only part, we're now interested in adding more biology and chemistry. You want to be able to simulate the carbon cycle. Instead of specifying how much carbon dioxide is in the atmosphere, instead you can specify what the emissions are, and then the model itself will simulate the uptake of that carbon dioxide by plants, the oceans, etc. You can end up with, on top of the physics, fairly complex in terms of computer representations, fairly simplistic compared to what kind of model you might use for an individual site, but representations of atmospheric chemistry in various processes, as well as simplified views of plant ecology, land use, carbon sequestration in the oceans and the atmosphere. So the models are getting more and more complex over time, but the goal remains the same. In order to come up with a simplified rendering mathematically of the global climate system so that we can perform what-if tests. What if this changes in terms of some radiative forcing agent? How might the system respond? So, when we think about the different factors, the different things that we need or may want to represent in a global climate model, mathematically, this figure kind of lists many, maybe not all, of the factors that are in there. And it's kind of there for eye candy, this figure, just to give you an idea that when we put these global climate models together, it takes a large number of people with a large number of disciplinary specialties. Right? We have ecologists and oceanographers and mathematicians and atmospheric scientists and chemists, and as time has gone on since I first came here back in the 80s, not only has the number of people involved increased, there's really been a big increase in the number of disciplines that are involved. We're looking to get a more and more complete modeling, a more sophisticated rendering of the global climate system. Now that has its pluses and minuses. Well, why would you want to keep adding additional factors? Well, a lot of these factors are involved in feedbacks. They help determine the climate sensitivity to change and its resiliency. So including them in the model allows them to have feedbacks which then interact with other parts of the system. Yet, just because we know that something exists that has a feedback, if we don't know how to quantitatively represent it, then we're not going to be able to put it in the climate model. So as we learn enough and actually come up with a credible representation, then such factors become nominees to be included in the next generation of climate model. But at its core, we can just go back to the basic physics. So we take the globe, we divide it up into millions of three-dimensional grid boxes. And we'll take a deep dive into that, but some of the models we're using here now have between 55 million and 75 million grid boxes. We're dividing the ocean, the atmosphere, sea ice, and land surface up into fairly fine grid boxes, much smaller than you can see here in the schematic in the lower right. And at the core of the model, think of it at the starting point, you take the equation of motion, the basic equations of motions for fluids on a rotating sphere, and take those things that you're used to seeing in the physics books and convert them in computer code, discretize it so it works on a grid. And that handles a lot of the large-scale circulation factors. But there's also a large number of things that matter to the Earth's climate system that you can't represent explicitly by those equations. Our grid boxes are going to be too large to trace things that matter. For example, if you want to close the heat budget and the water budget, you need to take into account the rate at which evaporation occurs from the ocean. But you can't represent each droplet or each wave or whatever and how that whole particular location is being involved in evaporation. So one needs to come up with a parameterization, some statistical representation that says, given these larger scale features of temperature, humidity, sunlight coming in, wind speeds, etc., this would be the rate that one would expect would occur over a grid box of certain dimensions. So that's what we would call parameterizations. And I mentioned before, increasingly, maybe about 50% of the global climate models being run today also have chemistry and biological components in them as well. So I think you can get an idea that this, I'm not going to take a deep dive, but this could get pretty complex. One of the last times I counted, I think our climate models that we run could be on the order of maybe 700,000 lines of code, something like that. And there's probably 2 or 3 lines of comments in there, but not so much. But basically, they're a lot more than a spreadsheet. So if you're used to coming from a realm of where your models are maybe purely statistical, more akin to a spreadsheet, this is a different type of beast, a different type of model in some ways, in that we do start from, we do have physics to fall back on and F equals MA. Okay, but the dynamical models is what these would be called, that are start with the physics, are often not going to produce the output, the results that you as climate impact researchers would use directly. It may be good for some of those mitigation questions to give a big, large-scale picture, but if you're interested in smaller-scale things or certain problems, you're going to find that GCM contains biases in it. Maybe for the place you're interested in the winter, the model tends to be a couple degrees too warm or too cold, and maybe it's as 30% too much or too little precip over the course of the year. et cetera. Its extremes may not be as extreme as observed. So there's going to be these shortcomings eventually in this model that is a free-running model. We're not plugging any observations into the global climate models, and it's simulating the entire world, not just the surface, three-dimensional atmosphere and ocean. So it's not going to be perfect. So a lot of times, this is something that the next speaker, Catherine Hayhoe, will be discussing, is that when there are applications for which the raw global climate model output is deemed inadequate, there can be ways of trying to refine it, to put add some value to it. And that can be done both by statistical means, commonly referred to as statistical downscaling, or there's also folks who do what's called dynamical downscaling or regional climate modeling, where you would create a finer resolution, higher resolution model that just covers the geographic area that you're interested in and have that be driven by the coarser resolution results of some of the global climate models. So when you're using results and you download results that may trace themselves back to some of the global climate models, it may very well be a value-added product that is presumed to be value-added, but then again, just how that refinement occurred will leave its own fingerprint on the data. Okay, so that's basically the same thing that I just said looking at one slide instead of two. But starting with coarse resolution climate model data spatially, and by melding it with higher resolution observational data, whether gridded or at individual stations, there can be statistical downscaling methods, which are often some of the data sets that folks use for the actual impacts research. Okay, back to the larger scale problem. One of the stumbling blocks we sometimes run into when discussing things is the difference between short-term climate and long-term climate. People talk about the difference between weather and climate. I like to pose it as we have initial value problems and daily weather forecasts and what are short-term climate outlooks, whether it's the forecast about whether or not there will be an ENSO, a La Nina or El Nino this year, whether this year we'll have an above or below active hurricane season. Those are initial value problems in that in order to have skillful forecasts, you need to have a good understanding about the way the system works. That can be in the form of a numerical model or something else. You need to have a good representation of understanding the way the system works. And secondly, it depends upon your starting point. And the goal is to take that starting point and predict how in detail the system will evolve, its ups and downs and movements from that point. And there's a limit to the predictability. The flap of a butterfly's wings, chaos theory, tells us that there's a reason why today we cannot predict whether in Lubbock on Labor Day we're going to have a thunderstorm or not. There's just a limit to the amount of predictability where small differences grow over time. And then the question comes up, well, if you can't predict whether there's going to be a thunderstorm in Lubbock on Labor Day today, how can you tell us what might happen 100 years from now? And that's because when we're looking at this multi-decadal, the century timescale problem, we can think of that as a different kind of longer-term climate problem. It's a forced boundary value problem, where for that, what we want again is a good understanding of the way the climate system works, based on physics and encompassed in these global climate models. But we're now not interested in what the starting point was so much. Instead, we're interested in how those forcing agents are going to change, those things that change the flow of energy through the atmosphere and how the system will respond, whether it's greenhouse gases or dust or changes in ground cover, etc. Now, in between, there might be some of you who are interested in kind of an intermediate time scale, say 5 years, 8 years, 10 years. That's a term that's commonly referred to as decadal climate predictability. And it's really an active field of research with a lot of open questions on it in terms of just how far one might be able to push the frontier having skillful forecasts on that 3, 5, 10-year time range. It's kind of a thorny issue, but the best results, I think, to summarize that are in there now, that probably with good climate models and a good observing system, perhaps one that's better than the one we have now, we can expect to see predictability of some large-scale features on those timescales. But will probably have geographic variations. There may be more skill in predicting Western European temperatures on those time scales than there are for the Central Plains, for example. So it's going to be a more nuanced field, and it's interesting and still developing. Okay, so back to that question that I tried to pose earlier to you, that if you wanted to make a better global climate model, how would you judge that? We talked before about model comprehensiveness. Now, a lot of people tell me, well, I don't know why you're asking the question, it should be pretty simple to figure out. The better climate model is if you were to take your climate model and, run it from 1950 until present, and compare that climate model's results with the observations, the one that has the smallest mean square error for the things I care about is clearly the best model. And that's a way that we do look at it, but it's not the only way. There's roughly an equal weighting given to model comprehensiveness, where for people who are really give a lot of weight to model comprehensiveness, it's making the model more complete, including more factors. If we know that there's something in the biosphere that has the ability to have feedback on the physical climate, then we ought to strive to add that to our model system. That is what makes a better climate model. The more comprehensive it is, the less simple. So what we can run up against with that is that as we increase the comprehensiveness of the model, as we include more parts, we're increasing the degrees of freedom. And that doesn't necessarily that we're going to converge to observations that way. It becomes a better test bed in some ways to study certain scientific questions, but it's not necessarily the way you would build something if you were just building a weather forecast model. There you're going to look at the RMSE. So one of the points I hope you can take away from this is that these global climate models that you may look to, their output or output derived from them, remember that they have been developed primarily as research tools to try to develop a better understanding of the way the climate system works, and to develop that understanding and then pose these what-if questions and see what the models have to tell us, and then compare it with observations and our underlying theory. They are not being developed primarily as forecast tools. So they're not they were not developed in order to be prediction models for your particular city. They're going to be used that way. They certainly, the output that they have can be leveraged in that way, but it's not their sole reason or even the primary reason for existing. I mentioned before, a lot of people are surprised about how much computer time we spend in the ocean, right? Couldn't you just make a better climate model by having finer spatial resolution in the atmosphere? Yeah, that takes computer time, but why are you spending so much computer time in the ocean? Well, this is one way to think about it. If you were from another planet and you were going to come to the Earth and try to figure out if it's gaining or losing heat as a whole, you'd probably be most interested in tracking the heat content of the ocean. The ocean's big, it has a high heat capacity, it moves slowly, but it moves steep. And so observational data sets show us that, over the last 40 years or so, more than 90% of the heat that's been gained by the planet it's in the ocean. So in that regard, in terms of the climate system, the atmosphere is an important part, but it's kind of the twitchy tail of the climate system, while the ocean is the big dog. So just to finish up, I've mentioned spatial resolution a lot, just to give you an idea of how closely tied it is to computer resources. So bigger supercomputers, faster supercomputers lead to better models. When I first showed up here at GFDL, this was the world's state-of-the-art global climate model. This was the checkerboard pattern from there. It shows the size of the grid boxes, roughly 4 degrees of latitude and longitude on the side. You can make out North and South America there in green. If we were to look at what we had developed by 2009, we were down from, instead of 4-degree resolution, down more to like 1/4 of a degree resolution. So just to see that a little better, if we zoom in on the Gulf of Mexico, by 2009, our ocean model surface grid would have looked something like that. Go back to 2004, it was about 1 degree. 1990s, 2 degrees. 1980s, 4 degrees. So clearly, computer power by us a lot in order to be able to have a better representation, but the spatial resolution alone isn't the key factor. One of the things that we've seen so far is while we are getting a finer look at the modeling and the results by the finer resolution, I can't think of right now any major finding from the 1990s that has been overturned as we've gone to higher and higher resolution. We're putting a finer point on the results and able to test additional hypotheses, but we haven't had any major reversals, such as, oh, now that we've gone to finer resolution, instead of having that kind of smooth look that we had a few years ago to the newer, higher resolution model, we're getting more details, but maybe we can take it as a positive that we haven't necessarily found sensitivities that have caused us to throw out old results. Results have been fairly robust. This is just to remind me that we change resolution not just in the horizontal, but in the vertical as well. We may be interested mostly in the surface climate, but what's happening in the lower stratosphere matters for us too. Okay, here's the final slide. Just people can give these talks, and this little anecdote. I try to explain things like this to some folks. I realize if it's not your cup of tea, it kind of be too much information pretty fast and too detailed. And so for my in-laws, at least, the part that they understand that they found interesting is not only were these global climate models interesting and used for science research, we actually had one of our images taken and ended up on a U.S. postage stamp. So if nothing else, sometimes you can get some interesting artwork out of it. So with that, I'll end here and turn it over to you folks if there's maybe good questions.
Thank you, Keith. So I think what we're going to do is people who want questions, come on up a little further into the room and, and ask, tell them who you are and ask the question. Say up for the camera. Who's going to start?
You can't see your face. Put your face up there.
Is that a good thing?
Yeah, we want to see your face.
Go ahead. Okay, Keith, we have a question.
Okay.
It's right there.
There you go.
Can you see it? Oh,
Yeah.
hey
Hello.
Keith, I'm Emily. I'm from the University of Arizona and I'm studying geography.
Okay.
And I had a question. You put up a diagram where you were talking about modeling the climate system, and you had this very small section about human influences.
Mm-hmm.
And I'm wondering how that's incorporated all into your climate models.
Okay, so the human influence part. So the three-step answer. Let me just do it. I'll try to do it quick. So the biggest way that human influences are incorporated into the models are through specification of changing amounts of radiative active gases, not just carbon dioxide, but in a typical model now there's more than 7 different greenhouse gases where those changing amounts are used as input to the model, and then we let the model determine its physical response to it. So greenhouse gases are specified either as concentrations or as emissions. That depends upon what flavor of model people are running. So too are short-lived species such as soot, sulfate aerosols, dust, and other features like that, all of which interact with either infrared or sunlight in various ways to change the flow of energy through the atmosphere. So that's one way that human influence is incorporated. A second way is that we also include, for retrospective experiments, we can include specifications about how land surface changes have occurred. You take a dark coniferous forest, chop it down, and replace it with a light-colored pasture. You change the albedo, changing the reflectivity. That will affect the climate. We don't necessarily have, some modelers will include projections for that in the future, but with this newer generation of climate models, instead of specifying those things There's actually vegetation models built into the global climate model, so the models themselves are computing when a forest might turn into a savanna, when a savanna might turn into a desert. So that way you get sometimes human elements are in there and sometimes not. And I guess a third way is that this is very much cutting edge, and I don't know that it's in many global climate models at this point. But there's also folks who are working on human effects on the water cycle, where some of these models will not necessarily resemble reality, is that we can have systems where once precipitation falls, it goes into the soil, but it tends to be modeled more as a natural system and not have all the dams and water releases and reservoirs in there. So if you're interested in river flows or something like that, the global climate models that have been run in the past haven't necessarily had that ability to do it. There's work going on now to try to see about getting that information and coming up with a way to incorporate it in the model so there can be a little bit more human influence in that way. But that's not there yet.
Other questions?
Hi, I'm Sarah. I'm a ecologist with USGS. And I was just wondering, sort of generally, you addressed this a little bit, but what do you think are some of the next big advances that you might know about or speculate about, or what can we see as sort of the next big thing?
Yeah, so I'll go on the two fronts. So from each generation of global climate model to another, we can just say that the generation period is about 5 to 7 years. They tend to improve in two ways. There's the increased spatial resolution. So additional computer power allows the grid boxes to be smaller, which once you get past certain thresholds, gives you new abilities. One of the things that we've seen here in these years is we can now run some climate models that are configured in a way where we might decide to put a lot of spatial resolution in the atmosphere and keep with a somewhat coarser ocean. And in that context, we run things that then can actually simulate spontaneously hurricanes, tropical cyclones, and you're actually explicitly creating Category 4, Category 5 storms. So that means for those impact researchers who are interested in questions about how might tropical cyclones change the changing climate, now instead of looking at coarse representation where there were tropical depressions and trying to extrapolate from that, we can now explicitly represent those in some of our models. Now those aren't going to be models that have multiple geochemistry in it, so we wouldn't be able to necessarily afford that, so there's different flavors. The other category we can go is that additional complexity. Sea level rise is a big question for a lot of folks. The interaction between land-based ice and the ocean around Antarctica and Greenland is pretty important. You know, the stability of ice shelves and the like. And the way ocean models were originally formulated, they just mathematically couldn't handle the idea of having these surfaces come and go that way. You had to parameterize how the tides were affecting the land-based ice above. So that's another thing that's an active field of research. It's a small community, but in order to try to get a better handle on the sea level question, there's a lot of work on trying to get the cryosphere, land-based ice, in there better. On land surface, say over the US, I'd say there's just a general increase in the refinement of the representation of hydrology is a continuing area where each generation it gets somewhat better. Whether it's going to meet the needs of the impacts researchers as well, each incremental step we get a closer and needed for some, but not others, depending upon their requirements. So that's another area of focus. A lot has to do with water resource management. So with higher spatial, the way they combine with higher spatial resolution, we represent the Rockies, for example, better, which then, especially for the western U.S., allows a better representation of snowpack, spring, melt, changes in that. And then if you have a better land surface, more sophisticated hydrology model attached to that, then you can actually start representing some of those flows down too.
Further questions? Yeah, Chase?
I have a short question.
Hey, I'm Chase. I'm a grad student in ecosystem science and management over at Texas A&M University. And I was just curious, what are the main programming languages you're using to build these models?
Okay, anecdote. So, I showed up here 30 years ago. Within my first week, there was a veteran programmer who told me this. Keith, I don't know what the programming language is going to look like when you're working here 25 years from now, but I know you're going to call it Fortran. Okay? And my response is pretty much what I hear, but here's how it came through. Because the global climate models push the limits of supercomputers. Back when I first started in the field, the computers that we were working with were serial number 2, serial number 3. I mean, it kind of defined the field. That's changed with commodity computers and parallel computing, but they still pretty much push the limits. These are extremely computationally expensive. Same for weather forecast models. So as a result, you need them to really perform. And back in the day, back when Fortran 66 was a language, that was the programming language that the people who wrote compilers focused on a lot for optimization. So if you wanted a language where you put in some extra time to construct it, you could perform those same calculations in maybe 1/10 of the time than if you were doing it in C. It was just developed, and it was the behind-the-scenes compiling experts that were building it that ended up getting the most performance. And even though the language that we program in today is Fortran, and it looks more like C did than when I first showed up, because it has the legacy, because it always needs to be backwards compatible and has that, it's still going to be called Fortran, I think, for a while. Analyses and other things are being done increasingly in Python and other things, but the core of the models is pretty much Fortran right now, for performance reasons.
Thank you.
Any further questions for Dr. Dixon? Yeah.
Hello, Dr. Dixon. I'm Casey Williams. I'm a research assistant here at Texas Tech in educational psychology. And I'm actually studying a lot about modeling, but in the framework of social science and behavioral research. And part of the disconnect between developing a model that's parsimonious and can explain a lot of the variability in any system is understanding conceptually a lot of the interconnected relationships that are there. And so I was thinking, you showed that picture of the of Buzz Aldrin. Do you have a relationship with astronomy and understanding space and time conceptually, very in a broad sense? And does that contribute to your models and how you develop more and more factors and create a better understanding? I don't know if I'm making myself clear.
I got a general idea. So I can answer a question and like map onto it. So when I talk about the interdisciplinary, the folks that it takes to create a model. Now, I work with people who got their PhDs in various parts of physics, including astrophysics and things like that. On a day-to-day basis, we aren't thinking about it so much, but we will touch bases with it. There are certain similarities. It goes a little bit back to that question that I had early on about what makes the better climate model. We can only include new parts. Right? We're always considering at one level, in the conceptual level, what factors are there out there that influence the climate, and then try to think about which ones explain the most variance and which ones we'll get to when we can get to, right? Which are the big ones, which ones are the next ones that matter. Just because we've identified some things that are factors that can influence climate doesn't mean we can include it in the model unless we have a way to represent it in a way that is credible. Otherwise, we could just add a new feature, but it's just adding noise to the system we're not really learning something. So there's kind of a tiered thing. So at one level, yeah, those sessions occur where very interdisciplinary, let's sit back and look at the model, where we can go from here, what's the next way, where we can make a breakthrough on it, what might need to be included. Somebody might argue better representation of the tides, some people might represent, you can go through all the various things, better representation of dust, better representation of ionosphere features. But there's a lot of different ways of going about it. Then the question is to figure out how big an effect it might have, and is it primed for being added into the model. So at one point, there's a broad community where the ideas are heard, and then there's kind of a funnel effect where you go from the theater of the ideas to kind of the pragmatic. Is this how we're going to spend these resources now, or is it something we might have to wait for the next generation or so?
Cool. Thank you very much.
I think we have time for one more question.
Thank you, this is Derek.
Oh, it's Derek.
And we have the red wagon in the corner too. So as far as decreasing uncertainty, I wonder if you could comment about the work Claire Dessner's done with the natural variability uncertainty. We have the model uncertainty and scenario, and are we running up against a brick wall with natural variability uncertainty?
Okay, so first question is: has the audience heard about Paradis's work, or are they not familiar? Do I need new background on this, Derek, or just by then?
Give a 30-second intro.
Yeah. Okay. So there's always going to be variations in the Earth's climate system, right? What we would call unforced, what you might call natural. Things just oscillate. El Niños are going to come and go regardless. Volcanoes, every so often, will blow their top with particles up in the stratosphere that will cool the surface for a couple of years, and they're not going to be predictable. So there's always going to be the variations. Then there's the flap the butterfly wings. You can take this global climate model, and the phrase from Ed Lorenz back in the days for a weather model, a flap of the butterfly's wings will be Brazil today could determine whether there will be a thunderstorm in Lubbock next week, right? There's this interconnectedness where small differences will grow and do that. So we can run our global climate models where we can keep all else being the same, except we can flip a few bits, change a few numbers, a small amount. Smaller than you could measure reliably with a thermometer. You could change the temperatures around the globe here and there, and you would see after time El Niños would come and go different times. And as they get projected on top of the forced climate signal, you're going to have a different look to the way the climate goes. The general envelope of things will go in one direction, but the details are going to be different. And the larger the spatial scale look at, the less those wiggles matter. You're interested in a given county or location, then those wiggles are really, really big. So the background is that if we try to reduce uncertainty, if the question is posed of how much will the climate warm in Lubbock by the year 2075, there's different sources of uncertainty. One is, what will people do? How much greenhouse gas emissions will there be in others? And that's not really a science question, that's a people question. The second part will be, even if we knew what that was, what could we expect the climate response to be? And that's where different climate models are going to give somewhat different areas. There's going to be an envelope of possibilities. They're all going to warm in assumptions, but whether it warm 3 degrees or 4 degrees or 2.5 degrees, that could vary depending on how you represent things in the model, so it gives you a range of possibilities. So there's sometimes a desire or thought that if we could get all the models better, they would converge to one answer. Right, so maybe on average, they would warm 3.5 degrees. But we have to keep in mind that there's always going to be this natural variability occurring at all time scales. So just day-to-day weather, El Niños are going to come and go, and there's also lower frequency variability. North Atlantic ocean can kind of go through some oscillations that can have an infrared elsewhere. Some of those things right now just aren't predictable. So that's another source of uncertainty that's going to remain. So, you know, in that framework, Derek, I'd say, yeah, there's going to be ultimately a wall in that natural variability, unforced variability is going to remain. That's one of the communications challenges we have. One of the things we saw with all this discussion about, oh, the climate hasn't warmed for the last 10 years. What about this hiatus that shows the models were wrong? Well, we expect the ups and downs to plateau every now and then. It's not unprecedented, so it wasn't such a big deal in some quarters. But we also haven't converted to having all those climate models start getting closer and closer together. And part of that reason is because we're also making it more comprehensive, including more factors, more features, and add more feedbacks. For one out of another, just think about methane is a greenhouse gas, powerful, stays in the atmosphere 10 years or so, but molecule for molecule warms more than carbon dioxide. Well, methane, if you take some of the permafrost up in high latitudes and it warms and it melts, whether the carbon that's in there, some of it comes out of carbon dioxide or methane, depends upon how wet the surface is and how much of it comes out and when does it come out, and those are tough things to predict. So, and that isn't something that we really have the ability to model with a high degree of certainty now. So expecting that the models were going to converge. If in the next generation of global climate models we saw an uncanny convergence, the one answer, I'd be suspicious. Because the uncertainties just in how to represent some of these scientific things is enough. That to me was kind of signaled that there wasn't much diversity in the way people were representing them in their models. That they kind of took one way and everybody followed the leader, as opposed to speculating and trying different things. F equals MA. Okay. What happens when you melt permafrost is a little different.
Okay, Keith, thank you very much for taking your time. Next time you're going to come